Okay, so I hope that you have now a full understanding for the sampling distribution of X bar, because I need to move on to the sampling distribution of another estimator, which is P bar. We remember we introduced that P bar or P hat, you can call it, okay, which was the point estimator for the proportion of the population. So again, in that slide where we have seen that when we collected 500 samples, which is something that we don't do, but just for the sake of discussion, we could see also that P bar was changing. So P bar is also a random variable. So we expect that it will have a mean, it will have a distribution, it will have a standard deviation, and also we're going to name that distribution is sampling distribution. Why? Because it's coming from a sample, that's it. But now it's called the sampling distribution of P bar, right? Which is the distribution of all possible values of the sample P coming from that population. So we're going to learn also these three characteristics of the distribution. What is the expected value of P hat? What's the standard deviation of the distribution? And what's the form of the distribution? All right, because we're going to use these in our inference. So let's see. We'll start with the easiest one. So as you can see here, the expected value of P hat, which is now our new variable, okay, it's a variable, it has so many values, but it has then, like any variable, it has a mean. So this mean, which called E of P hat, is equal to P. What's P? It's equal to this is the population proportion. All right, so when we select sample from population, we get the sample proportion. We know that this sample proportion belongs to a distribution that has a mean equal to P, which is the population proportion. For the P hat, similar to what we have seen in the X bar, standard deviation of X bar, that we have two relationships between the standard deviation of P hat and the population parameters. So if we have a finite population, all right, finite population, then we use the first one where we are multiplying this, which we know that we call it the finite population correction factor, and we are multiplying it by square root of P, which is the population proportion, and we multiply by 1 minus P, we divide by the sample size. While if I have an infinite population, it's simply that part, which is the right hand side in the first equation. Okay, so let's see in which case we're going to use that simple form. So here also we have similarity with the previous distribution. So we're going to use that simple form, okay, when the population is infinite, obviously, or even when it is finite. However, also as we did before, we consider that the population is large enough if its sample size, if it's the population size, capital N, is greater than 20 times the sample size. And also we're going to call sigma of P bar the standard error of the proportion distribution. So let's find this for our AAI example. We know that the population proportion is 0.6. So, and we already established that 2500 is large enough, and this is our criterion. It's greater than 20 times 30. So we use the simple form. So it's simply square root of P 1 minus P, where P is the population proportion. Here we go, 0.6 times 1 minus 0.6 divided by the sample size. Okay, and we get 0.0894. Finally, about the form of the distribution of P hat. What does it look like? So we're going to approximate its distribution as being normal distribution in two conditions, or when two conditions apply. If n times P is greater or equal than 5, and, okay, so both conditions should apply, n times 1 minus P is greater also or equal than 5. So please be careful. Whenever you want to answer questions about the proportion distribution, you have to make sure that you test these two conditions. And only after you find that MP is greater than 5 and N times minus P is greater than 5, then you can use the normal distribution for P hat. Otherwise, you are not allowed to do that. All right, so let's apply that on EAI example where the director is wondering that when he collects a sample of 30 managers from the population, what would, and find the proportion of that sample, what's the probability that the sample proportion is within 0.05 from the population proportion? Okay, so what do we have here? Let's see. N times P is 18, greater than 5, great. And N times 1 minus P is 30 times 1 minus P, which is 0.4, so 12. So these two conditions tell me then that P hat belongs to a distribution that is normally distributed, okay? And I know its mean equal to the population proportion, and it has a sigma of P bar. And we have already calculated these in the previous slides. Okay, I know that the mean of that population is 0.6, and we just found the standard deviation. So now I can see that on the graph, okay? And the question here on the graph is, what's the question can be translated in a probability statement like that, right? That P hat is within plus or minus 0.5 than the population proportion. And now I can plug the value of P that I know, and I can simplify. So this is my question, in fact. Okay, what the probability that P hat is between 0.55 and 0.65. So we go to the graph and we locate these. And to answer this question, we need to find this area. Also, as we learned before, to find the area between two values, we find the area of or the area from the lower tail to the upper value, and we subtract the area, the small area. Okay, so this is what we're doing here. And what do you think is the next step? I hope that you could guess. Now we standardize. So here I need to take some time just for you to make sure that you understand everything. When we standardize, we subtract from the value of the variable. In our case, it's P hat. We subtract the mean, and we know now the mean of the population of this distribution is P, and we divide by the standard deviation. That's it. So nothing changed from what we did in the previous topic. And on the right hand side, we have a specific value 0.65, which is this one, okay, or which is this one, minus the mean divided by standard deviation that were calculated. So now we have a probability statement in Z terms. We look in the Z table and we find these probabilities, and we get 42%. Okay, again, it's a not bad probability. Okay, so let's consider now increasing the sample size from 30 to 100. What would change in the distribution of P hat? Again, the form does not change, the mean does not change, but what changes is the standard deviation. Okay, so now the new standard deviation, because it's function of n, so this the only parameter that will change. Now we have 100 instead of 30, which makes our standard deviation 0.049. Okay, so what can I tell now about P hat? We know that, first let's do the test again because n changed, and we know for sure that it will pass the test because n increased, did not decrease. But anyway, we'll do that, and now we know that it's normal distribution. But look at this, also I put it in bold just to that you pay attention that this changed from the previous example, and this is the only parameter that changed. And now I can put my question again in probability statement. I will replace P with a value, and I simplify. So this is my question. Next, I'm going to standardize. So subtract the mean. Now I do it. Subtract the mean, divide by the standard deviation, and look at here. note that this has changed from the previous calculations, which will change also my z-value that will be there. Now I have z-values of 1.02, okay, which is the answer for that ratio. Looking at the table, we find the area and we can see that now the probability that the sample mean has a proportion that's within plus or minus 0.05 from population mean has increased from 42% to 69%. So quite a good improvement here due to the increasing the sample size.